Okay, so this is yet another Paxos. This time it's Swift, and it's for fast geo-replicated state machines. The authors are some researchers in Italy and France, and the paper was published and presented at NISD this spring. So they are optimizing for geo-replicated consensus. And why do we need another consensus protocol? What's wrong with Paxos? This one is optimized for high latency. So you've got nodes spread across the earth. We're expecting reasonable throughput, but every round trip is very costly. So the goal is to minimize network hops at all costs. The baseline here kind of is MultiPaxos, where there's a long-lived leader, and the client sends its request to the leader. The client is responsible for finding the leader somehow. And the leader broadcasts the client's command to all the replicas. It commits the command once it gets a simple majority of replies, at which point it can execute the command, figure out its result, and send the result back to the client. SwiftPaxos is an attempt to reduce network single direction latency in the comment case. So in SwiftPaxos, the client sends its request directly to all of the replicas at the same time. And when the leader hears from 3/4 of the nodes and they all give it the same information, in other words, they tell it to put the same command in the same slot, then the leader can then commit and execute the command and reply to the client. So this saves a single one-way network latency. Why 3/4? I tried really hard to understand this when I did the Nezha presentation a few months ago. I understood it then. I have forgotten. I tried to remember. I failed. So everybody just assume that it's 3/4 is the size of a fast quorum, and that avoids certain problems that only a majority would have. But SwiftPaxos, you can have conflicts. Since different clients are all broadcasting simultaneously to all of the replicas, replicas can receive commands in different orders. And so some of the replicas could tell the leader, I want command C1 in slot I. Others could say they want command C2 in slot I. How do you resolve that? You have to fall back to the slow path. And so the fast path is faster than Paxos, but the slow path is actually slower than Paxos because you first do a fast round, it fails, and then you do a slow round. So there have been various follow-ons to SwiftPaxos which attempt to avoid conflicts. And there are various conflict avoidance strategies. There is ePaxos, which I think we've covered in this group, but I haven't read it in detail. But ePaxos is leaderless. In ePaxos, each node tracks each command's dependencies. And it waits until, so it's constructing a graph of dependencies among the commands. And each node waits until a strongly connected component of the dependency graph appears. You can read the papers to find out what that means. It means that it can resolve cycles and all the replicas will execute all the commands in the same deterministic order. Nezha, which we covered more recently. It's pretty similar, except that it introduces deadline ordered multicast, which depends on reasonably synchronized clocks. It schedules each command to run sometime in the near future and hopes that on 3/4 of the replicas, the same set of commands will arrive before their deadline. So that will reduce conflicts that way. Nezha also falls back to a slow path when deadline ordered multicast makes a mistake in ordering. But also Nezha has the insight that different orders are okay among non-conflicting commands, which are also called commuting commands because their order doesn't matter relative to each other. So there's also an aspect of dependency tracking in Nezha, but it's not the main approach to conflict avoidance. And now we have SwiftPaxos. Once again, replicas are tracking the dependencies among commands, but in SwiftPaxos, unlike ePaxos, there are never any dependency cycles. So you don't have to wait for a certain amount of the graph to appear before you can resolve cycles because there aren't any cycles. And we'll discuss why in a few minutes. And SwiftPaxos, like Nezha, it ensures that all replicas for a set of conflicting commands execute them in the same order. But commuting commands can happen in any order. So there's more concurrency and less coordination in SwiftPaxos. SwiftPaxos, unlike ePaxos, it has a leader, but the leader is mostly needed for accelerating the slow path. The leader's responsibilities are a little bit tricky, so we'll talk about that. And here's the link to my review of Nezha that I did for this group. I think that was earlier this year. And there's a video there too. So what I found helpful for understanding all of these systems is to ask, what decree are replicas agreeing to? So in Paxos and MultiPaxos, the decree that we're achieving consensus about is that command C is in slot I of some ballot B. So we're saying, put this command in exactly this position in the total order. Whereas in ePaxos, everybody's agreeing that the command C with the sequence number S, it depends on the commands in some set. So there's no actual order that everybody is agreeing to, that the consensus system is agreeing to. It's after consensus, all of the replicas look at the dependency graph that they have agreed to, and then they resolve cycles using these sequence numbers in order to deterministically execute the commands in the same order, sort of a partial order, where conflicting commands all have the same order. So order is part of the consensus protocol for Paxos and MultiPaxos, but not for ePaxos. And then in Nezha and SwiftPaxos, what we are all agreeing to is that the command C depends on some set of commands. So once again, we're creating a partial order, but the consensus protocol is not ordering the commands. It's only agreeing to the dependencies. All right. When can a replica run a command? So in Paxos and MultiPaxos, as soon as the command is committed, all the commands it can depend on are already committed because it's already placed into a total order. In ePaxos, a command can run after its dependencies have run, and there are special rules for breaking cycles. ePaxos a command might wait for an unbounded amount of time, I think, before it can actually run. And so this is the big problem with ePaxos, is that a adversarial workload can just blow up the size of these strongly connected graph components, and you can never actually run anything. In Nezha and SwiftPaxos, you don't get cycles, and so after commands dependencies have run, or after they're committed, there is a bounded amount of time before this command can actually run. In SwiftPaxos, the leader is semi-strong. There is a leader, it's stronger than ePaxos, but it's not as strong as in MultiPaxos. This semi-strong leader, there's one leader per ballot, and it's just, you just take the ballot number modulo the number of replicas, and that number is the ID of the leader, and it remains leader until failure. I think that this is how classic Paxos also works. And each slow quorum is a majority of replicas that includes the leader. So that's something special that's about is that a majority is not enough to commit a command. The majority must include the leader. And then the fast quorum, kind of weird. It could either be 3/4 of the replicas, including the leader, or you could pick some unique fixed quorum that's a majority, and it also must include the leader. So it's either 3/4 or a specially designated majority. And the user can decide which kind of fast quorums they want when they configure the system. And the trade-off is that if it's any 3/4, then it's more fault tolerant. Or you can just choose a unique majority, and that's faster. But if any member of that majority goes down, then you need to do some sort of recovery. And you can read section 5.5 for all the complicated trade-offs between these two configurations. The big takeaway here is every quorum includes the leader, but clients can propose to any replica, and this seems to me to be a particular quirk of SwiftPaxos, that leaders have this kind of role. So, all right, let's talk about the algorithm already. How does it actually work? So in the fast path, a client sends the command to all the replicas. This is the same as in FastPaxos. And then each replica does the following. It computes the command's dependency set, which is all of the prior uncommitted conflicting commands. So prior, meaning this replica has received some uncommitted command before C. Uncommitted, so you only need to worry about a command's dependencies if those dependencies have not been committed yet. And they must be conflicting. So for example, if the command C reads some key X and there's an uncommitted write to X, that uncommitted write is a conflicting command with C. An uncommitted write to some other key Y would not be conflicting. It doesn't matter what order you read X and write to Y. So those would be commuting commands, so you don't worry about those. So once this replica has looked through its uncommitted commands to see which ones conflict, those are C's dependencies, and it broadcasts that dependency set to all the peers. And then this replica waits for a fast quorum of messages about this command C from its peers. So the client talks about C to all the replicas, and the replicas talk about C to each other. And if this replica receives no agreement among a fast quorum of peers, then it falls back to the slow path, which I'll talk about later. Or if there is agreement, then we go to the fast path. So on the fast path, we wait for the conflicting commands to commit, and then we commit C. And then we wait until all of C's dependencies are executed, and then we execute C. So it could be we wait to commit the write to the key X, and then we wait to actually execute that write to X, and then we execute a read of the key X, for example. So here's a figure from the paper where we've got 3 clients, and these circled replicas, P1, 2, and 3, they are a fast quorum. And we're doing the weird configuration here where we've got a specific special majority designated as the fast quorum, and the fast quorum includes the leader. So you can see in the timeline that there's a particular order of, it looks like Y, then X, then Z. But because of the geo distribution, the clients have different latencies to the different replicas. And so each of the replicas gets these commands in a different order from the other replicas. So for example, replica 1 gets X, then Y, then Z. And replica 2 gets Y, then X, then Z. And replica 3 gets Y, then Z, then X. So everybody's got a different order. Does this mean that everybody's conflicting? No, because some of these commands commute and some of them don't. So the outcome of these 3 orders is that everybody agrees about a Y. When they received Y, they looked at the contents of the command itself and saw, for example, P1 decided that Y does not conflict with X. And so Y has an empty set as its dependencies. P2 and 3 didn't have to think at all because they had no prior uncommitted commands at all. And so they also decided that Y's dependency set is empty. All right, so everybody agrees about a Y. For X, there is some disagreement. It arrived before the other commands on replica 1, so its dependency set was empty. It doesn't conflict with the command Y. So on replica 2, its dependency set is also empty, but it does conflict with Z. And so when it arrived after Z on replica 3 decided that Z is in X's dependency set. So it has a different opinion from the other 2 members of the fast quorum. And since we've decided that these 3 replicas are the special members of the fast quorum, if there's any disagreement among them, then we can't take the fast path. So there's a disagreement, and we have to use the slow path for command X. And then I won't go through it in detail, but Z has the same outcome where because it arrives in different orders, it's before some conflicting commands on some replicas, after some conflicting commands on other replicas. That means that Z also has to take the slow path. So, and by the way, people, this was a tough paper for me. So if you think I'm making a mistake, please just jump in either on the chat or just turn on your mic and interrupt, because I'm kind of winging it here. So commands X and Z have to take the slow path because no fast quorum agrees on their dependency set. What is the slow path? The slow path is just normal Paxos. The leader proposes its value for this command's dependency set, and then we do normal Paxos agreement with a normal majority. The kind of funny thing about this fallback is that we're doing it within the same ballot. So that means that replicas can propose both a fast proposal and a slow proposal for the same command in the same ballot, where the slow one is more authoritative. Yeah. So this is simpler than ePaxos, believe it or not. And why? Uh, and I think that it's because ePaxos commits commands in any order at all. In ePaxos, a command's dependencies must all be known before it commits, but its dependencies need not be committed yet. And so that's how ePaxos ends up with cycles and why it needs to build up a certain kind of subgraph before it can start executing commands. In SwiftPaxos, um, it waits to commit a command until after all of its dependencies are committed. And this is why there are no dependency cycles. And that's why the wait time for a command between proposal and committing and executing, it's bounded. And the amount of state that replicas have to keep about uncommitted commands is also bounded. I didn't understand that, by the way, until I read the proof in the appendix. So if you really want to understand this and you don't yet, and you haven't read the appendix, maybe that will fix it for you. Also, SwiftPaxos, after a leader change, it has this whole recovery protocol, which is more complex than either the fast or the slow path. In the recovery scenario, there can be cycles. And so SwiftPaxos does have a cycle breaking algorithm, but it's only in the recovery protocol, not in normal execution. And side note, by the way, I wonder if it would need that if it just used raft elections where a member of a majority with the longest log was elected. Maybe it wouldn't have cycles then. That would be an interesting follow-up question. Their evaluation, I kind of like how they did it. So they have sites scattered around the Earth, and there are replicas at some of the sites and clients at some of the sites, and some of the clients are co-located with replicas. So some sites are better than others if you're a client. The best site, which is the middle graph there, the client has the least latency of any client to a fast quorum of replicas. And so it often gets a fast quorum agreement on its commands. And so it gets very low latency. And it beats the heck out of all of the other protocols that they compared it to. The worst site down at the bottom, the client is not very close to a fast quorum, and so it has higher latency, and its relative speed up compared to the other protocols is not as good. And in fact, there's this KERP plus protocol, which I don't know anything about, but it seems to do very well in this situation. And then the average site, which is the top graph, SwiftPaxos is still good, but the client is sort of farther from a fast quorum than on the best side, but closer than on the worst side. And the speed up is also kind of in between. Yeah, so the other way that they evaluate within the same chart is the cumulative distribution function of latency. So this previous chart, the x-axis here is the conflict rate. So 0, all the commands commute, 100%, all the commands conflict. You can see that SwiftPaxos's performance is kind of declining down towards that of the other protocols as the conflict rate rises. The other evaluation that they do, the conflict rate is 2%, and fixed at that. And so now you get to compare latency as a cumulative distribution function. And so you can see again at the best site, SwiftPaxos is the best. And then a couple of the other protocols are actually better at this 2% conflict rate at the worst site where the client is very far from a fast forum. My feeling about this paper is it was well written, although the protocol is complex. And as you can tell, because I don't know ePaxos that well, it was hard for me to understand. My feeling is that people have said to me that ePaxos is just not practical because of this unbounded state accumulation before you can actually execute commands in certain workloads. And so it's like interesting research and often cited, but not practical. And that maybe SwiftPaxos is a practical extension to the ePaxos research, but it's a new paper, and so we'll have to see how the community kind of responds to it and builds on it. And also, like I said, parts of the proof in the appendix are worth reading. If I hadn't read them, I wouldn't understand why SwiftPaxos avoids cycles, whereas ePaxos has to deal with cycles. And that is that, and I'll open the floor to the group. Thank you.